So the group that worked on the question from section 4.2 was asked to simplify this expression that involves some exponents. So where were the sticking points on this problem? What were the things that you screwed up when you did this problem the first time, and how did you fix them? Somebody from the club's group. Tell me about it. Yeah, Angela. Right. So my experience with these problems is that where people are most likely to screw up is in the very first step, where you focus rightly on this combination of expressions, 2 times the quantity negative 3x squared y raised to the second power. So what should you do first to that expression? What has been done first in going from that step to that step?
Solve what's inside the parentheses.
Right, so look inside the parentheses, ask is there any way to make that any simpler inside the parentheses, and there the answer is no. So we can't simplify inside the parentheses, but there are 2 different operations of arithmetic happening to the quantity in parentheses. We have a 2 out in the front, and we have a 2 out here in the end. So which of those 2's does its business first? What operation is right here in between the 2 parentheses? Multiplication. And what operation is this 2 doing? Squared. It's an exponent. So which of those operations should happen first? Order of operations. That's a constant companion in algebra is the order of operations. It tells us that exponents must happen before multiplication in simplifying an expression. That's why in the work that's up here, what you see is that each of the 3 factors that are inside the parentheses are getting squared first, before that 2 that's out in the front multiplying this expression does anything. This 2 out in the front is just on the outside looking in while all the squaring happens. So the x squared, when we square it, becomes x to the 4th. Why? What did you do to these exponents to get x to the 4th? Where'd the 4 come from? This 4 right here? Yes, right. We multiplied the exponent by the power that we were raising it to. When you raise a power to a power, the exponents multiply. So x squared raised to the 2 power is x to the 2 times 2. Y raised to the 2 power is y to the 1 times 2, y squared. Where does this 9 come from? Yeah. Negative 3 squared, exactly. Negative 3, the quantity squared. So when people mess this first step up, usually it's because they try to distribute the 2 in here and get a negative 6. Or sometimes just in the process of squaring negative 3, people will write negative 6 accidentally instead of 9. But 9x to the 4th y squared is a correct rendition of that first step. Once that happens, then you can multiply the 2 into this monomial, which combines the 2 and the 9 to give you 18. Okay, and then what's happening at this last step? What are these little arrows that are drawn in between these 2 sets of factors? Sierra, what did you mean by these arrows here?
You combine the like terms.
Right, so you look and combine the like, I would call them like factors because they're being multiplied. But yeah, so you're looking for the powers of a common base, right? The powers of x combined together, x to the 4th, and x to give you x to the 5th. Why is it x to the 5th? Where does the 5 come from? Adding the exponents. Because what is the exponent on this x right here? 1. 4 plus 1 gives you the 5. Likewise with the powers of the common base y, right over here, y to the 2nd times y to the 4th gives you y to the 2 plus 4, y to the 6th. And then, of course, because I'm devious, I also put this extra plus y here at the end. What happens to that plus y? Yeah, how come we can't combine it with the rest of the expression that's out here at the front? They're not like terms. And terms are important in that discussion because we're trying here to add. And anytime you're adding, those expressions are terms. And if they're not like terms, that means that we can't combine them to make a single term out of them. And so at that point, we have to stop. So this problem really does have a little bit of everything that can trip people up about working with exponents. But step 1, don't forget that order of operations. The exponent on the outside of the parentheses has to be taken care of before the multiplication that's out in the front. And then after that, remembering that multiplying powers of a common base is the same as adding their exponents, and that any attempt to add powers can only be simplified if they're like terms, which these two are not. So in this problem, the question just asks you to multiply this pair of polynomials together, t minus 1 times t to the third plus t squared plus t plus 1. Who was it that worked on this one at the board? That was Brittany. So tell me about your process. What did you do here?
I don't like the foil, so I did the box thing.
Okay.
But,
Yes.
you put like one of the set of parentheses on the top and one on the bottom, and then you multiply like across, and then if those squares like that are diagonal line up, they cancel out. So then you're left with just t to the fourth minus 1.
Okay, so this is the grid or the lattice approach to multiplying polynomials one by another. I like this way myself because it makes sure that we don't forget any potential products of terms, right? We had here a binomial, something with 2 terms, multiplied by a polynomial with 4 terms. And so in the end, we're going to end up with 8 different products to add together. And making this little grid makes sure that you don't forget any one of those 8. Because the alternative, to use FOIL in the so-called horizontal method, is just to kind of draw out these little connecting arrows between each pair of terms, one from the first factor and one from the second factor. And then just, be really careful to make sure that you get all 8 of them. Having the table makes it a little more visually obvious when you've accidentally forgotten a term. So you end up with these 8 different products, and then the goal is to add all those 8 different terms together. And when those 8 different terms got added together here, Brittany was noticing that some of them canceled one another out. For example, we got a t to the third power from multiplying t and t squared, but then we also got a minus t to the third power from multiplying t to the third by negative 1. And when those two add together, the coefficient becomes 1 minus 1, or 0, t to the third power, which is the same thing as not having a t to the third at all as one of our terms. So, as you were saying, those t to the thirds end up just canceling out. And the same thing happens with the t squareds, the same thing happens with the t's, and the only thing that survives this process is the t to the fourth at the beginning and the minus 1 at the end. The only modification I would make to what you said was that the terms that cancel or the terms that combine together are not necessarily always found like diagonal to one another. You might have to look a little bit harder to see where the like terms are. But just remember that like terms are the name of the game once again, once you're adding everything together. Combine the like terms by adding the coefficients. The Hart's question was a question in which we had to factor this expression written here on the top. And so the first thing that was done is to look at the 3 individual coefficients, 48, 16, and 32, and determine their greatest common factor. And looking at the factor trees of all of these things, we found that each of those coefficients has 4 powers of 2 in common. And so what does that make the greatest common factor of these 3 numbers, these 3 coefficients? 16. Because it's 2 times 2 times 2 times 2. So that explains why, in the first step, the coefficient 16 was factored out of this expression. And when the 16 was factored out, where did this 3, this 1, and this 2 come from? How did you know, for example, that this should be a 3a squared b to the third here in the first term? Where did that 3 come from? Yeah, that 3 is there because it's the result of taking the original 48 that we started with and dividing out that 16, which is the greatest common factor. So that explains where that 3 came from. Another way to do it that requires even a little bit less thought, which is occasionally a good thing, is that 3 is exactly what wasn't highlighted when we accounted for the greatest common factor of 48, being 16, which included all the other 2's, including the one that's kind of cut off here, 2, 2, 2, and 2. So all 4 of those 2's were taken care of, but that 3 is the one prime factor which wasn't accounted for in the factor tree, right, once we matched up all the 4 powers of 2. So whichever way you prefer to see that is a way that it will work. I like the dividing way also. So then what about this ab squared that came out at the end here? Why is a to the first power the right number of a's to bring out of this factorization? That's right. Each of these three terms has at least one power of a to choose from. And b squared because each of the terms at least has two factors of b to choose from. What's the shortcut? How do we figure out how many powers of, let's say, b to take out of these three terms? What's the quick way? If we look across all three of these terms, why do we know that b squared is the right number that we can factor out? The quick and dirty way? Always remember that when you're finding the greatest common factor of a pair of monomials, you're going to choose the one with the smallest exponent on each given variable. So in our three terms, we had b to the third, b to the fourth, and b to the second. Of those three choices, we're going to choose b to the second. It's the smallest exponent, because that means that each one of these three terms has at least two powers of b that we can take out. And then likewise for the a to the first. Okay? That between the a to the 2, a to the 1, and a to the 2, 1 is the smallest exponent that we can take out. So in the diamonds problem, you were asked to solve this equation for x. And of course, what's interesting about this equation is that it has a second power of x in it, right? It's not just a simple linear equation like you can use with the reverse order of operations on, like we could have solved on exam number 2. This one is something brand new. So somebody from the diamond squad, tell me what your reasoning was here. It looks like in the first step, what'd you do? What did you subtract, and why? Yeah, Jenny.
We subtracted 24x and 90 to get everything on the same side.
Okay, and that is an excellent idea. So you subtracted 24x from both sides. You subtracted 90 from both sides. And the goal of all of that was to make it so that all the variables are on one side of the equation, right? So all terms to one side, which is always a subtractive process, right? Never a division or anything like that. And so the only issue that I have with this is that it looks like your equal sign disappeared when you did all that subtraction. So what should I have here? Equals what? Yeah. So that's the biggest thing that I see is missing from this solution up to this point, is that when you've subtracted all these terms to one side, you still have an equation. It's just that the other side of that equation is 0. And that 0 is so important that I can't possibly waste enough breath overstressing how important it is to get that 0 on one side of an equation when you're trying to solve an equation like this. Because everything else that you do from here on is not going to help you solve this equation unless the other side of that equation is 0. So now I'm going to carry this 0 down. Equals 0, equals 0, equals 0. So that what we do next will make more sense. But we'll get there when we get there. Once we realize that we have now an equation still that has a 0 on the other side, what happened on step number 2 here? What'd you do? Factored. And what did you factor out? Here, what you factored out was really the greatest common factor of those three terms, which is 2. So you factored the 2 out, and you were left in the middle with x squared minus 12x minus 45. Okay, but now that you see x squared minus 12x minus 45, a light bulb goes off. You say, hey, I think I might be able to factor that too, which is what looks like happened next. So where did your factorization come from? What's going on here with this 15x and this 3x? Exactly. So you played the little sum and product game. You're looking for a pair of numbers which, when you multiply them together, you get negative 45. And when you add them together, you got negative 12. So thinking about the multiplication part first, the possibilities for 45 are what? 45 and 1, 15 and 3, 9 and 5, and then I think that's it. These are the only possibilities. But one of them's got to be negative because we want negative 45 to be the product. And if you're looking for that pair which adds together to give you negative 12, you'll find it in negative 15 and 3. So that's where this negative 15 and this 3 come from in the factorization that then follows on this. So you factored out the trinomial, and you got x minus 15 times x plus 3. But we still have an equation to solve. And here's where it's so important that we had 0 on the other side, because what's the last step? It's the step that I saw written down in your papers, but I'm not seeing it written up here on the board. What happens now that you've factored this expression?
You have to do 2x minus 15 equals 0 and 2x plus 3 equals 0.
Yeah, so what you're looking at here on the left side of the equation is a product of two terms, of two factors, 2x minus 15 and x plus 3. If a product is equal to 0, then it must be the case that one or the other of those factors must itself have equaled 0. So this is the split and solve step in the process. Right? We give each one of these factors its own equal to 0, and then we can solve the equations that result. Dividing this first equation by 2, I'll get x minus 15 equals 0. Adding 15 to both sides will give me x equals 15. And then for x plus 3 equals 0, what do we do to solve it?
Do we have to have the 2 on there or no?
Yes and no. Let me get to that as soon as I write this last little bit here. All right, so the 2 that I have written out here is a little bit optional. Let me say why that is. Because there's a 0 on the right-hand side of this equation, solving 2 times something is equal to 0 is the same as solving that thing equals 0. We could see it as dividing this equation by 2 on both sides, but 0 divided by 2 is still 0. Or, if we wanted to be really fancy, we could have seen this as a product of 3 factors instead of 2 factors. And one of the equations that it would give me if I broke it into 3 pieces is the equation 2 equals 0, which doesn't actually give us a solution. That's interesting. So whether you choose to have the 2 as part of this or whether you choose not to, you'll end up with the same solutions either way. So this problem's got a lot going for it. There's, first of all, the priority of getting all the terms onto one side so that 0 remains on the other side. Then it's a matter of factoring, which happened in 2 steps. First, factoring the greatest common factor out, which in this case was 2, and then using the sum and product game to factor the trinomial. But once we get it down into this factored form, and we have a 0 on the other side of the equation, that's when it's appropriate to break it apart and solve each of the simpler equations separately. Here we end up with 2 solutions, x equals 15 and x equals negative 3.